Hey, we're back. In this video, we're going to cover doing a one proportion z-test for population proportions. So I know the way they've redesigned the curriculum for some of you who are coming from another book, it might be a little confusing if this is the right video, but if you're one of my students, this is 9.2. A little bit of warning here. I am awfully sick right now. So if I have to pause and not cough into the microphone for a minute, and you'll figure out what's going on. All right, so performing a significance test about P, so lowercase p referring to the population proportion. So we still have to check our conditions when we're doing these significance tests. That's why we made such a big deal about them in the previous chapters. So the three conditions that we have to check are that they should be pulling random samples from the population of interest, and then the 10% condition must be met, meaning that the sample has to be smaller than 10% of the population of interest. And the large counts condition must be met, where both n times, now this is a little interesting for notation, it says p sub naught and n times 1 minus p sub naught. They're referring to the population proportion that we're using in our null hypothesis. And we got to make sure both of those counts are at least 10. So 10 successes and 10 failures, if you want to think of it that way, at least. Oh, here's the note about that. So because we're assuming that the null hypothesis is true when we're performing the significance test, we use the parameter value noted as p sub naught when checking the large counts condition. And that's also the same value that parameter that you're going to use when you do the statistic when you're finding the standard deviation or standard error. Oh, I feel like I'm going to have a coughing fit, so if I have a weird video, that's why. Okay, for a test, use the null value of p sub naught, not the sample proportion, p hat, when you're checking the large counts condition. That is the expected count for failures and successes. Have to be at least 10, which we kind of just talked about. All right, so here we have an example. According to the Census Bureau, the proportion of students in high school who have part-time jobs is 25%. An administrator at a local high school suspects that the proportion of students at her school who have part-time jobs are that proportion is less than the national figure. So she would like to carry out a significance test at the 5% significance level. So remember, we learned in the previous section that we have to state the significance level before we do all our data collection as good statisticians. We don't try to manipulate that just to make our data work. And P is the true proportion of all students who have part-time jobs at the school. So within all of the students at the school, she takes a random sample of 200 students and finds that 39 of them have part-time jobs. So first we're going to check the conditions because that's what we have to practice first. And this is something that we would literally have to write out on any sort of a free response question. So we'd have to get used to the what we're writing. So is it random? It does state here that she carries out a random sample. The 10% condition. Now this one kind of bothers me because you don't really know how big the school is. They just say it's like a large school. So I think the best way to state that, because we're just going to, frankly, this is not the right way to do it, but we're just kind of assuming the 10% condition is always met when it's vague like this. So we would say something like it's reasonable to assume that 200 is less than 10% of all the students, meaning that there's like 2,000 students in the school at least. So if you find that unreasonable, I'm sorry. The large counts condition. So notice how they set this up, and you would have to write this out the same way, showing the silly math. I know you don't feel like you have to show it, but you do on the free response. So n times p sub naught, so the population proportion that we're testing against. So 200 times 25% is 50, which is surely more than 10. And then for failures, that would be 150, which is also more than 10. So we've checked all the conditions. And, well, apparently we're moving on to a new problem. So a basketball player claims to be an 80% free throw shooter. You think the player is exaggerating. So the null hypothesis is that his true proportion is 80%, and the alternative hypothesis is that it's less than 80%. So if the null hypothesis is true, then what values of p hat should we expect in a random sample of 50 shots? So they're going to go through some things here on this question, and they're going to try to tie you back to the normal distribution next. And that's the whole point of this, because we're going to perform a z-test. So shape, because the large counts condition is met, the sampling distribution of p hat will be approximately normal. Now they didn't go through and show the large counts condition, I think we've actually done this question on a previous lesson, if memory serves me correct. So they would have done, 50 times 0.8 and 50 times 0.2, which are both greater than or equal to 10. And then the center, remember from our previous work, the mean of the sample proportions would be equal to the proportion of interest, so 80%. And then variability would be calculating our standard deviation here. So notice what they're using here is the P sub naught, so the proportion of interest. This guy, they're not using like something out of 50 here. So calculating this, it comes out to this lovely decimal. And what we're going to find out soon is that when they go to find the z statistic and show it by hand, they actually just leave this in the formulaic look. And I'm going to be honest, I kind of cheat. I set it up and I pretend like I'm going to be using like my table A, but I don't actually use table A. Oh, don't tell anybody. Okay, so they're going to draw the normal distribution. Remember, we defined it to be normal or approximately normal because of the large counts condition. So here we have a mean of 0.8, and then they counted up and down with that standard deviation. And this is the sample proportion of made free throws, p hat. So if a player makes 32 out of 50 shots, that particular value is 0.64. So if we were to draw that on the normal curve, here we are, and then that point and down is what they're looking at here. Now, where did that 32 out of 50 come from? Again, I think this was a previous example that we were looking at in a previous lesson. So what we're going to do here is we're going to standardize that value and this entire curve, and we're going to find the z statistic. So this is, we're going to learn in a moment on our calculator, it's a one proportion z test. So this is going to be our z statistic, our standardized statistic. So p hat is that value we just found. So the 32 out of 50 was 0.64 minus the proportion from our null hypothesis divided by that guy, which again came from this formula, and it comes out to negative 2.83. So that is a standardized test statistic. Ugh, really end up talking really funny in this class. Sorry, guys. And that measures how far a sample statistic is from what we would expect if the null hypothesis were true. And remember, that's always what these significance tests are battling against. You always assume the null hypothesis is true until you find evidence that you can reject it. So there the formula is in words, which I really like, and I think that's the way it looks on our formula sheet. I really need to have one of those next to me during these lessons, my bad. And you see the two standard normal curves next to each other. This one has to have this really explicit title, and you notice this one doesn't. It just says z-score. So this is one of the reasons why when people are doing free response questions, they like to use the test statistics, which you have to identify anyways. It just makes for labeling the curves a lot nicer. Like you don't have to sit here and add this weird standard deviation. You can just go 0, 1, 2, 3. So now what we're going to do is we're going to use our normal distribution calculations to find the p-value. You can either use table A or the calculator of this probability here. So negative 2.83 and less. Now, if we're looking at the sample proportions and didn't standardize them, you still could do that. But what we're going to find is we're going to go through the effort of finding the standardized test statistic anyways, and it shows up on our calculator anyways. So it's a nice double check. So if I were going to flip to table A and look for a z-score of negative 2.83, and remember table A measures left, it would give me a probability of 0.0023. If I was to use technology, now they went ahead and just used the standardized curve. So something really super small, doesn't matter, but something super small to negative 2.83 with a mean of 0, standard deviation of 1, and looky there, you get the same value. So now we're back to that part-time job question. Remember the administrator selected a sample of 200 students, found that 39 out of the 200 did have a part-time job, and we already did the conditions check on the previous couple slides ago. So now we're going to answer some other questions. Explain why the sample result gives some evidence for the alternative hypothesis. Well, the alternative hypothesis is that the proportion is actually less than 0.25. So if we calculate that sample statistic, p hat of 39 over 200, that's like 19.5%, which is less than 25%. So that is evidence as suggested by the alternative hypothesis. So that's some evidence for it. But we don't have convincing evidence yet. We have to do some more work for that. So what we're going to do now is calculate the standardized test statistic and then find the p-value. So this is what I mean by like, you're going to have to do it anyways. And in a moment, I'll show you the calculator where you can actually set it up like you're going to do it by hand and maybe do it by hand, but actually check it on the calculator, which is a glorious moment in math when you know you have something right. So notice what we've done here. So we've used this formula from, really, you pulled it right off the formula sheet, but you probably will end up kind of memorizing it. So this was the p hat minus the population proportion, and then the standard deviation formula here, and it comes out to negative 1.8. So if we were to draw that on a standardized normal curve, and they left off a label here, it should have said z-scores here, but they did say z equals negative 1.8, so I think they would have got credit for it. Notice what they're coloring in here. It's everything. Remember, the alternative hypothesis was it was less than 0.25. So you're trying to figure out if your value, or even more extreme than that, what's the probability of that occurring? So we are going to go to the left as well. And if you use table A, that comes out to 3.6%. If you use technology, it also comes out to 3.6%. So our final answer is, what's the conclusion? So because the p-value is 0.0359, so 3.6%, and that is smaller than our significance level, we reject the null hypothesis. So this is the statement we have to make sure we have written down. We have convincing evidence that the true proportion of all students at this large high school who have a part-time job is less than 0.25. Okay? So we had significant evidence to reject the null hypothesis, and that's why we are making that claim. So it's a 4-step process, and it's really important that you do all 4 steps. And I don't care if you go what you find to be little kid style, where you like literally write out step 1, step 2, and you identify them in your work. In fact, I'd prefer it if you do. In fact, I might write your test that way. I might say state and then a big empty space. State the hypothesis that you want to test and the significance level and define any parameters. And then you're going to plan it. You're going to identify the appropriate inference method, which I know today doesn't sound like a good question because you're like, what are you talking about? We've just been doing the same thing over and over again. That's true for today, but as we learn some other significance tests, we're going to have to identify which one we're supposed to do. And then check our 3 conditions. Remember, random, 10%, and large counts. And then actually do it. So find the sample statistic, give the sample statistics, calculate the standardized test statistic, wow, and then find the p-value, and then, of course, conclude, make your conclusion. So do you have enough evidence to reject the null hypothesis, or do you not have enough evidence to reject the null hypothesis? Now, I really like this next slide, because the next few slides, because it really tells us why we're doing those 3 conditions, and I think this helps me. This might become a poster in our classroom. So the random condition just ensures that p hat minus p sub naught is a good estimate for the difference between the true value of p and the null value of p. So the fact that we've randomly selected them means that we don't have bias in our selection process. The large counts condition allows us to use the normal distribution. So the fact that we can do, 10% of uh, no, I said the right thing, that we have at least 10 successes and at least 10 failures. That means that we are able to say this is approximately normal and use our calculations for a normal distribution, thus the z statistic calculation. There we go. Now the 10% condition. That's what allows us to use this formula for standard deviation. It's familiar to us because we used it before in sampling distributions. And because we are sampling without replacement, as long as we have the right type of sampling, it's okay. Like, we know it's not independent necessarily, but it's okay. So here's a nice slide that gives some good pictures. This is what your curves should look like in general for your alternative hypothesis options. So your alternative is either going to say the true proportion is greater than the null hypothesis or less than the null hypothesis, or in some cases it'll just say not equal to. Now in the case where it says not equal to, you're going to see a split two-tail sort of curve where we're going to have to take the area of each of the tails and add them together, or simply multiply the one you find by 2. I think I missed something on there. No, I think we're good. All right. Oh, back to the potatoes. Remember these potatoes? So recall we have that potato chip producer that we met in section 9.1, and the main supplier agree that each shipment of potatoes must meet a certain quality standard. If the producer finds convincing evidence that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load of potatoes. Otherwise, the entire truckload will be used to make the potato chips. Potato chip producer has just received a truckload. A supervisor selects a random sample, so ding, there's random, of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes. Is there convincing evidence at the 10% significance level that more than 8% of the potatoes in the shipment have blemishes? So remember your 4 steps here. We've got our step 1, which is to state. So that we have to state the significance test. Our null hypothesis is that our proportion is equal to 8%, while the alternative hypothesis is that it's actually greater than 8%, where P represents the true proportion of potatoes in the shipment with blemishes using a significance level of 10%. So this is where they define their parameter and their significance level. Very necessary in the state part of it. So now our plan, and I know this seems weird to you right now because you're thinking, oh, why did I have to say this? Because it's the only one I know. Yeah, so far, the answer is so far. So we're doing a one sample z-test for proportions. And random condition, it's stated clearly that this is a random sample of 500 potatoes. The 10% condition, and this is a good way to state it, because I don't really know anything about potato shipments, but I think it's reasonable to assume that 500 is less than 10% of all the potatoes in the shipment. So basically, do you think they're getting at least 5,000 potatoes in a truckload? I think that's a reasonable statement. And like I said, we're kind of cheating on this. We're just assuming it always is met. So just check that one. But you still have to state something. And then the large counts condition. Assuming that the null hypothesis value is true, 500 times 8% is 40, and 500 times 92% is 460, both of which are greater than or equal to 10. So now we're on the do stage. This is where you have to show your math, and I know it's obnoxious, but you do it anyways. The only thing they're missing here is they didn't draw a curve. They should have drawn a curve, but whatever. P hat is 47 out of 500. That's the random sample that they chose. Now, first thing to notice, they didn't notate this, but just in your head, okay, that's 9.4%. That is evidence in the direction of the null hypothesis, or sorry, the alternative hypothesis. And that's important thing to note because sometimes kids will set up the alternative hypothesis in the wrong direction. So if your statistic doesn't even give you evidence, that means you've set something up that's wrong. All right, so now we're going to go find the z statistic. The 0.094 minus 0.08 divided by that hot mess, and we get a z-score of 1.15. Again, I would have loved if they'd drawn a curve, but they didn't. And remember, our alternative hypothesis is that it was greater than 8%. So your curve area that you're trying to find is from that point and greater, because you want to be at least that extreme or more. So remember table A, if you're using it, measures to the left. So if they found 87.5%, they have to find 1 minus that to find the left side of the curve. If you're using technology, man, it would be brilliant to just use the standardized statistics that you have here. Hey guys, don't forget, let's say you did like 10 of these problems in a row, the mean and standard deviation are always going to be 0 and 1 if you standardize, which you are. So that's kind of nice. It's a bit of a time saver because you don't have to keep changing out all those values in your calculator. I'll talk about the calculator more in a moment. Now the p-value comes out to 12.5%, which is greater than the significance level. So remember the rule, if the p is small, reject the null. So in this case, we don't have enough evidence to reject the null hypothesis. So we're going to say there is not convincing evidence that the true proportion of blemished potatoes in the shipment is greater than 8%. That's our conclusion. There we go. There's the calculator. So on your distribution menus, there's something called a one proportion z-test, which is what we've been doing. So they took one random sample, created a proportion, and remember we've been calling this a z-score, so this is a z-test. There's other ones on there, I know. You're like, what are all these things? We're going to learn about them later. So they're going to ask you in these, this is the newer calculator screen. The older calculator, gosh, I think you have to remember the order in which to type them in. And I think on the older ones, they only do left bound, but the newer one's real nice. So if you are using an older calculator, just reach out to me and we'll figure out how to get it entered on yours. But it does ask for piece of naught, which is the proportion of interest from the null hypothesis. The X is the number of potatoes that they sampled that were bad. The N is the total number of potatoes that they sampled from their sample proportion. And then this is what I love. They let you choose what kind of alternative hypothesis you're looking for. So is it not equal to, less than, or greater than? Remember ours was greater than 8%. So then you even get to choose your color. How cute is that? We're going to go to calculate. Draw will literally give you a drawn version of it on a graph, which is really quite nice if you're trying to match, or if you have to create your own drawing. Some of us are just visual people, but you'll notice even on the drawing menu, it gives you everything you need. It gives you the Z statistic and the p-value, which is the probability of that shaded region. So if you're a visual person, I think this is a great screen to look at for draw. Some of you don't like that and you just want the data, so you'll do calculate. It's up to you. Anywho, the moral of the story is we still have to go through all that work on a free response question. If it was multiple choice, game on, man. You can do whatever you want to do for that problem. But if it's free response, they're going to want you to show all that work of finding the test statistic, the z-score, and drawing it and making all those claims very clear. So, more is better in that case, I guess. For me personally, like I said earlier, I will set it up. And if I have time, I will actually calculate it by hand. But I'm also going to use the calculator to double check because that's what it's there for. Now, some AP exam tips here. When a significance test leads to fail to reject the null hypothesis, be sure to interpret it as we do not have convincing evidence for the alternative hypothesis. So that's the phrase, we do not have convincing evidence. You can say I failed to reject the null hypothesis, but you still have to give context, of course. If you say anything that sounds like you believe the null hypothesis is true, you're going to lose credit. And this is kind of like when you're involved in a court trial, they say guilty or not guilty. They don't say innocent. They don't say the defendant is innocent because that's not something that they just don't have enough evidence to say that they are guilty. So that's the idea you can't say we accept the null hypothesis. You just say we fail to reject the null hypothesis. So this statement here about there is convincing evidence that the true proportion is 0.08, don't write that. That's naughty, naughty, naughty. And I need your young people to tell me, what does FTR mean? Like, seriously, for the record? I don't know. I don't think young people say for the record, so someone's going to have to help me out with that. Okay, another exam tip. You can use your calculator to carry out the mechanics of the test, but there's a lot of risk involved in that. If you just use the calculator with no work or one or more of your values are incorrect, you're going to get no credit for the do step. So if you opt to use the calculator only method, you still need to name the procedure. So you'd have to state, I'm using a one sample z-test for proportion, and you'd still have to report the z statistic and the p-value, which I don't think is that hard, but it's also not so hard for you guys just to write the math out. See, I've heard of them doing this. I don't know if it's true, but I've heard of this from other readers. If a child has performed the wrong significance test, but they did it and they showed all their work, they actually get some credit for that question, which is kind of awesome. All right, here's a check your understanding. Now, I think I was really nice on this chapter. The check your understanding, the questions, they're going to take you a year and a half to write down. So if you have my slides, I went ahead and gave you the answers to this. But I still want you to stop and think about them on your own before you cheat and look at the answers. So, according to a national campaign to prevent teen and unplanned pregnancy, 20% of teens aged 13 to 19 say they have electronically sent or posted sexually suggestive images of themselves. The counselor at a large high school worries that the actual figure might be higher at her school. So, to find out, she administers an anonymous survey to a random sample of 250 of the school's 2,800 students. So all 250 respond. Wow. And 63 admit to sending or posting sexual images. Carry out a significance test at the 5% significance level. So we're going to use our 4-step process. First, we're going to state. We're going to state our significance test. So we want to test the null hypothesis that the proportion is equal to 20%. And our alternative hypothesis is that it's actually greater than 20%, where P is the true proportions of all teens at the school. Notice that's at the school, that's the population, who would say that they have electronic, now this is really critical, who would say they have electronically sent or posted sexually suggestive images of themselves using alpha of 5%. This phrase right here, who would say, has to be in your answer. I know that seems really picky, but that's what you're testing and that's what you're claiming at the end of this. Okay? Because if you were to say something different other than who would say, you're actually talking about a statistic and not a parameter. All right, plan one sample z-test for P. So that's the test we're using. It's clearly stated she randomly sampled the 250 students. The 10% condition is met because 10% of 2,800 is 280, and we've done less than that. And then the large counts condition says that we'll have at least 10, successes and failures, if you want to think of it that way. But 250 times 20% and 250 times 80%, those are both greater than 10. You still have to show the math there, and I know that's really obnoxious, but you have to show it. So now we're going to do it. We're going to find the we're going to find the proportion of the sample she took. So 63 out of 250, which is 25%. Already that is evidence towards the alternative hypothesis, so I feel like we're setting this up right. And obviously we are, since this is the book answer. And then we're going to find our standardized test statistic. Wow, I cannot talk. So that 0.252 minus the 20% divided by the standard deviation comes out to 2.06, which if we draw the standardized normal curve, and these are z-scores, you're going to see this. We want to do everything this extreme or more. I hope you can't hear my kids fighting upstairs. Sorry, guys. All right, so if we're using table A, now remember, table A measures this point down, so you have to do 1 minus this value you're going to get. Either way, it comes out to 0.0197. This is the other reason why we make you draw the curve. If you didn't remember to use table A properly and you just gave this value, you'd have 98 point something percent, which clearly this is not 98%. Now, using technology, again, it's just preferable that you use the standardized version of normal CDF, where the mean is 0 and the standard deviation is 1. Either way, it comes out to about 2%. So we got a pretty small p-value just now, and it is smaller than the significance level of 5%. So that means we are going to reject the null hypothesis. We have convincing evidence that more than 20% of the teens in her school, here's key, would say that they have electronically sent or posted sexually suggestive images of themselves. And that is a very sad case study. I'm going to move on from that. All right, let's talk about two-sided tests. We haven't talked about that yet. So far we've just seen one-sided ones, and the area in the tail is the p-value. Well, that's true for two-sided tests as well, except because you got two tails, you're going to find the area of one of the tails and you're going to double it, and that would be the value for p. So, according to the Center for Disease Control, 68% of high school students have never smoked a cigarette. Yan Hong wonders whether this national result holds true in her large urban high school. For her AP Statistics class project, Yan Hong surveys a simple random sample of 150 students from her school. Okay, if you can hear my kids, I swear they're having fun. They're so loud, though. She gets responses from all 150 students. That's not my finding, but that's fine. And 90 of them say they have never smoked a cigarette. Is there convincing evidence that the CDC's claim does not hold true at Yang Han's school? So, four-step process, just like before, we are going to state our null hypothesis is that the proportion is the 68%, but the alternative is this side, it's not one-sided, it's just going to say that's not 68%. So she's not going one direction or the other. So keep that in mind. Now, if you're thinking about the ramifications of this, because she's going to have to double the area of her tails, it's going to be harder to reject the null hypothesis because her p-value is going to be double what the one-sided test would be. But sometimes it calls for a two-sided test like this, so it just is what it is. Now, she did state the p is the proportion of all students in Yang Hong School who would say that they never smoked a cigarette and will use a significance level of 5%. So for the plan step, we're using a one-sample z-test for proportion. It is random because she took a simple random sample of 150 students. The 10% condition was met because it's reasonable to say that 150 is less than 10% of all the students at her school. That means she would have like 1,500 students at her school in total, which I think is reasonable. And then the large counts condition is met because both of the success and failure numbers come out to greater than or equal to 10. So check, check, check. And now we're going to do. So the proportion of her sample is 0.6. Now, right away, you're like, oh, why didn't she do a one-sided test and just go less? Because that's just not what she was testing. She just wanted to know if it was different. She can do more investigation later if she thinks it's one side or the other. So she's going to find the z-score associated with that statistic, and it comes out to negative 2.10. She's going to draw the curve, and then she's going to remember, oh, I did not equal to the 0.68, which means she has actually what's called a two-sided test. So positive 2.10 would be the other side of this curve that is of interest to her. Now, it turns out because of the symmetry, the area under this side is the same as the area over here, so she just has to double that area. So if she's using table A, it comes out to 3.6%. And if she's using her calculator, now this calculator did a one-sided and doubled it. If you remember on the screen I showed you before with the calculator, you can do a two-sided test where it says like not equal to the null, and you don't have to double it in that case. So on those newer calculators, you do have an option to do a two-sided test. Either way, the math comes out to 3.6%. So remember, we are testing at a 5% significance level. So since our p-value is less than our significance level, we're going to reject the null hypothesis. We have convincing evidence that the proportion of all students at Younghung School would say they have never smoked a cigarette differs from the claim of 68%. Now, key phrase here, underline this. Who would say that they never smoked a cigarette? Okay, they need you to say that, and they're going to make a big deal about it here. When making a conclusion in the significance test, be sure that you are describing the parameter and not the statistic. In the preceding example, it would be wrong to say we have convincing evidence that the proportion of students at the school who said they never smoked differs from the CDC's claim. Because if you say they said they never smoked, you're referring to a sample proportion. But that's not what we were making a claim about. We were making a claim about her entire school, which, we didn't sample everybody. So we have to make sure that they say it gives convincing evidence that the proportion of all students at the school who would say they have never smoked. I know that sounds super picky. It just is what it is. So this is kind of fun. There is a link between confidence intervals and two-sided tests. So a 95% confidence interval, if you remember our work in the previous chapter, that coincides with a 5% significance level. Any value outside of the confidence interval would be rejected as implausible. So confidence intervals are really kind of nice because they give you like an acceptable boundary. Like we would accept claims or values between here and here, and anything outside of that would be garbage basically to us, and we would reject. This is a two-sided test at a significance level can be found by a similar confidence interval. There's a question coming up in a moment where they show you a computer printout of a confidence interval, and they're going to ask you like which one's better, doing a two-sided significance test or doing a confidence interval. Oh, like right now. Okay, so we have a National Institute for Occupational Safety and Health. Job stress poses a major threat to the health of workers. No kidding. And this was written before COVID, guys. A news report claims that 75% of restaurant employees feel that work stress has a negative impact on their personal lives. Managers of a large restaurant chain wonders whether this claim is valid for their employees. So they take a random sample of 100 employees, finds that 68 say yes when they were asked, does work stress have a negative impact on your personal life? So the question is, did the data provide convincing evidence at the 10% significance level that the proportion of all employees in this chain would say yes differs from 75%? So again, I gave you the answers on your slides. Pause the video and try this if you don't have those. But up top here, we're going to state the test. We are going to use a null hypothesis that it is 75% and an alternative hypothesis that the proportion is not 75%. Where P is the true proportion of all restaurant employees at this chain who would say that work stress has a negative impact on their personal lives using a significance level of 5%. 5%? I thought they said 10%. I think that's a 10%. Yeah, that was a typo. That should be 10%. Anywho, um, one sample Z, we're going to use a one sample Z test for P. We have a random sample of 100 employees, so that's the random part, 10%. It's reasonable to say that 100 is less than 10% of all the employees at the restaurant chain. It was 10, right? 100, yeah, okay. And then the large counts condition that we would have, more than or equal to 10 successes and failures. So according to our data calculations, and we're going to show it, right, on the paper, we're going to have 75 when you do n times p, and then n times 1 minus p is 25, both of which are greater than 10. So there's the three conditions met. So now we're going to do it. We're going to find the statistic. 68 out of 100 is 0.68. And then we're going to calculate the standardized test statistic, and then we're going to draw it, and we're probably going to cheat a little bit and use our calculator, but that's okay. We're still going to show the work. So either way, we are going to find out that the area for both of these tails, when you either double one of them or add them together, I guess is another way to do it, comes out to 0.1052. So that is greater than the 10% significance level that we were working with. So in that case, we're going to fail to reject the null hypothesis. We do not have convincing evidence that the true proportion of all restaurant employees at this large restaurant chain would say that work stress has a negative impact on their personal lives. It's different from the 75%. Now, again, that was for a two-sided significance, a z proportion, one proportion z test. If they wanted to go one direction versus the other, like for instance, that statistic they had was less than 75%. If they did the one tail, they would be getting a 5% or so. But, would you still keep the 10% significance level in that case? And then the answer to that is probably not. Either way, it didn't matter. That's not what they're asking us to do. All right, so question 2, we have this mini tab output for a significance test and a confidence interval from the restaurant worker problem above. Explain how the confidence interval is consistent with, but actually gives you better information than the significance test. So the significance test, here's all the data here, blah, blah, blah. Here's the test itself. That's kind of nice. Here's the confidence interval for the 90% level, which coincides with our significance level of 10%. So if I do a confidence interval for 10%, acceptable values fall between 0.60 blah blah and 0.756 blah blah, which our test statistic was 68%, which does fall within that 90% confidence interval, which means it's acceptable, meaning I wouldn't reject the null hypothesis. It gives you the same exact information, the z value and the p value. But why is it better to look at the 90% confidence interval? Well, the confidence interval tells you every single thing that it would accept, like a range of values, and a significance test will only test for one particular value. So if for some reason you were having a whole bunch of statistics that, different samples that you were trying to look at, and you'd have to do more than one significance test, like, no, thank you. But if you had a confidence interval, you would at least have a window of values. And you will notice, those of you who've taken AP biology, is they really like using confidence intervals because for the math of it, it's just easier to look at. Like, okay, anything in this range is good. So when we go to apply statistics to real life things, you got to think about who's working with these statistics. People who have a very deep math background might not like looking at significance testing. Like, it's a lot to think about. But a confidence interval is something that we all can kind of accept and understand pretty easily. All right, power of a test. I think this is towards the end here. Researchers often perform a significance test in hopes that they will find convincing evidence for the alternative hypothesis. That's kind of the point of them. Now, the power of the test is what we're going to talk about next. Researchers would make what's called a type 2 error, remember from 9.1, if they failed to find convincing evidence for the alternative hypothesis based on the data. And what they mean by that is they didn't find convincing evidence, but turns out in real life it actually should have been rejected, the null hypothesis. They should have found convincing evidence, but they didn't. That's called a type 2 error. How likely is a significance test to avoid a type 2 error? Well, that's referred to as the power of the test. So what's the probability that your significance test will avoid type 2 errors is the power of a test. That's the idea. Oh, and there's a key part here. When a specific alternative value of the parameter is true. They have to tell you that something is true in order for us to find the power. Now, good news, you don't need to worry about calculating the power of the test. And these problems are going to be given to you, or they'll give you something else that we can figure out the power, but you're not going to have to calculate the power of the test. The power of the test, oh, we've seen this battery problem before, haven't we? So they want to know about the battery life for these guys, 30 hours of continuous use on average, and blah, 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 simple random sample of 50 AAA batteries, and we'll use them continuously until they're drained. They want to perform a test at the 5% significance level. The null hypothesis is that the mean is 30. Now you might notice that they are using mean and not proportions here. That's okay. You're going to find out that this works the same way. Mean is the true mean lifetime in hours of the deluxe AAA batteries, and the alternative hypothesis is that it's actually greater than 30. So they want convincing evidence. So they're going to give you this next question says the power of the test to detect that the mean is 31 hours is 0.762. Interpret this value. So if the true mean lifetime of the company's deluxe AAA batteries is 31 hours, that means there's a 76.2% probability that the company will find convincing evidence for the alternative hypothesis. So this is the specific value that they have to give you. This is the power of the test, and this is how we interpret it. So the probability is pretty good that they're going to avoid a type 2 error, is what's happening here. Now, this is the only thing they might have you do for calculation regarding a power of a test. So the power of a test in the previous example, it's the probability that you reject the null hypothesis given that the mean is 31. So that was something they would have to give to you unless they phrase it as this. So a type 2 error probability is simply the complement to the power value. Now that kind of makes sense because the definition of the power of a test is the probability that they will avoid a type 2 error. So the complement of that would be the probability that they will make a type 2 error. So in this case, the type 2 error, there's a 23.8% chance of that. So here's some formulas you might need to think about. They might give you the power and they want to know what the probability of the type 2 error is, or they might give you the type 2 error probability and then you got to go figure out the power. So it's not crazy calculations you'll have to do. They're actually pretty nice. So what can researchers do to decrease the probability of making a type 2 error, which thusly will increase the power of the test? So the power of significance test to detect an alternative value of the parameter when the null hypothesis is false and the alternative is true, based on a random sample of size n, a significance level of A will be larger when. Now that was a mouthful, guys. All they're saying here is, how do we increase the power of a significance test? Well, here's how you can do it. You can increase the sample size. Or you could increase the significance level. Or the null and alternative parameters values are farther apart. Okay. So this next question, we're going to quiz you. They're going to say like, well, which one of these would increase the power? Or would it increase or decrease the power? And explain. So Alzheimer's experiment. We had the drug that we're testing, and the claim is that fewer than 10% of patients who take the new drug for treating Alzheimer's will experience nausea. So the null hypothesis is that it is equal to 10%, and the alternative is that it's less than 10%. So P is the true proportion of patients, like the ones in the study, who would experience nausea when taking the new Alzheimer's drug. So again, that statement of P represents, who would be getting nausea when taking the new drug, not who did get nauseous. Earlier we mentioned the power of the test to be, oh, did we? This must be from a 9.1. The power of the test to detect a p-value of 0.08 using a random sample of 300 patients at a significance level of 5% is 0.29. So the power of this test is actually very low, 0.29%. Determine whether each of these following changes would increase or decrease the power of the test. So if we used a significance level of 1% instead of 5%, would that increase or decrease the power? So if we change the significance level to something smaller, it's going to decrease the power of the test. If you use a smaller significance level, it's going to make it harder to reject the null hypothesis. So That was not the right move if you were looking to increase the power. So the next example, if the true proportion is 0.6 instead of it being 0.8. So that makes it more extreme, right? So that's going to increase. It's going to be easier to detect a bigger difference between the null and alternative parameter values if you've changed that value. If you remember, um, oh, I guess they didn't go that far. Never mind. Ignore me. And then the third one, if they use 200 sample size instead of 300. So if they've decreased the sample size, they've actually made the power worse. They've decreased the power of the test. The smaller sample size gives less information about the true proportion P. Now, keep in mind, if you have decreased the power, that means you've increased the probability of a type 2 error, which is not great. But also what you've done is you've decreased the probability of a type 1 error. So we talked earlier, like in a previous lesson, about sometimes I would rather make a type 1 error versus a type 2 error, or the opposite might have been true depending on the context of the problem. All right, can a 6-month exercise program increase total body bone mineral content in young women? A team of researchers is planning a study to examine this question. So the null hypothesis is that there's no change, and then the alternative hypothesis is that there is an increase, meaning the mean is greater than 0, where the mu is the true mean percent change during the exercise program. Again, I know they're using mean instead of proportion. I know, it's okay. It's the same idea. So, the power of the test to detect a mean increase of 1% using a significance level of 5 and n equals 25 subjects is 0.8. Interpret this value. So if the power of the test is 0.8, that means if the true mean percent change, blah, 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 during the exercise program is 1, there's an 80% probability that the researchers will find convincing evidence for the alternative hypothesis that there was a difference or whether there was a change. So you have to start this interpretation here with if the true mean percent change is something. This is the determined value that they gave you. All right, question 2. Find the probability of a type 1 error and the probability of a type 2 error. So type 1 error is easy. That's just the significance level. So a probability of a type 1 error is equal to the significance level of 5%. But the probability of a type 2 error, remember, is the complement of the power. So there's a 20% probability of making a type 2 error. Describe 2 ways that researchers could increase the power of the test in question 1. So remember, there's 3 ways that you can increase the power of the test. One of them was to increase your significance level. That would increase the power. It also would increase the probability of a type 1 error, but it decreases the probability of a type 2 error. So, it's a trade-off. You could change your sample size, and you could have a different parameter value that was further away from the population. So this is what they came up with from the book answers. The researchers could increase the power of the test by increasing the significance level or increasing the sample size. They didn't touch the parameter issue because that just wasn't something they could do in this problem. So those are the 2 ways that they could increase the power of the test. I think that's it. Yay! All right, really long lesson. Really important lesson. Again, this was all about 1 proportion z-tests. I know they threw in some sample mean problems in there, but the idea of powers of tests and probability of type 1, type 2 errors, those kind of go hand in hand with whether it's a proportion or a sample mean. Either way, we're going to come back to that again and again and again. The next lesson is going to be, I think it's about the 2 proportion z-tests, I believe. So if you're looking for that, it's 9.3. All righty.